I'm sort of looking for a sport to encompass all three of those eating, drinking, and running one day. So yeah, good afternoon. I hope you had a good lunch. I just wanted to sort of intro myself, just to set the tone and give you a bit of context of who this guy is at the front. I'm from Bristol in the UK. For those who aren't familiar, it's about 120 miles west of London, as everyone sort of knows where London is. So I've been writing software for about 10 years. The last 5 sort of focused on Android. I've recently switched to Android freelancing, but sort of by day I'm a developer. But I kind of have an interest in mobile security. So a couple of years ago, I got involved in co-authoring the Android Security Cookbook. And even though that's a couple of years old, there's still some sort of relevance with stuff that you can use today. And the other thing that I'm sort of involved with is I'm an organizer and I was the founder of a local group called SW Mobile. And at the southwest of the UK, we run sort of mobile meetups with about iOS and Android. So that's kind of me in 3 bullet points. And here's today's presentation in sort of 2 lines. It's really geared towards Android developers. And you know, I've included a padlock, so you know you can trust this presentation, whatever I say. But yeah, it's really a story of kind of improving an app's security, focusing on the minimum effort to give you the maximum impact. It's not about creating a 100% secure app. It's about what are the small steps that we can do. And this is kind of based on an experience I had working on an app last year. And it was a kind of inspiration for this talk. We'll refer to it as kind of the Acme Corp app to sort of save me from getting sued and the client from being embarrassed. But yeah, let's pretend we're talking about Acme Corp. So to sort of set the scene for this kind of app, I'm sure we've all kind of worked with. It's a bit of a generalization. We've all worked with project managers, clients, stakeholders who don't get things like unit testing, code quality, and security risks. Their focus is always time. You know, project managers are they don't understand why it's important. Why is it going to take extra time? You know, why I've got deadlines to meet. The client and the stakeholders, they don't understand the risks. You know, of these security risks, and certainly they don't want to pay for them. You know, we can't let their that negativity stop us from making a secure app. You know, they'll say, you know, it's okay. You know, we're using SSL already. You know, we're not taking credit card details. We're not storing nuclear launch codes. So, you know, we don't need your security requirements, Scott. Your Fort Knox level security, as they always kind of call it. And this is always my reaction when they sort of say, oh yeah, we're using SSL. That's all we need to do. And you know, ultimately, I think this comes down to it. You know, it's our reputation as developers. You know, it's on the line with every app that we write. You know, every app that we put into our portfolio, and we talk to fellow developers at conferences like this. You know, if those apps are hacked, then you know, it reflects badly on us, regardless of if we've raised this early on in the project. I feel it kind of like massively, having co-written a book in security and, you know, talking at conferences about security, that, you know, if the stuff that I've worked on isn't sort of at least above the basic stuff, then you'll either just walk out or call me out on it. So that was a kind of, you know, that's to try and explain my mindset when with how things went. So, you know, what can you do? You've tried to convince the stakeholders that the money they'll lose, their job that will they potentially lose. I guess you could try and get them to sign something to absolve yourself of risk. But what I decided to do was take a leaf out of Shirley Booth's book and just do it. So I decided to sneak in these security enhancements. And I guess it's the opposite of a backdoor. So is that front window? I don't know. But that was the inspiration for this talk, and that's what we're going to kind of go through. So I kind of split the work down into what I called sneaky sprints. And that roughly kind of coincided with the kind of work we were doing on the app. The start looking at the API code and the the parsing stuff. So I sneaked in some security enhancements around that. Next, looking at the device and the data that it was storing, and then lastly, closer to publishing time, the APK once it's kind of live and on customers' devices. So again, this is work that I'm kind of sneaking in to the contingency of other tasks with top up in lunchtimes and evenings. So we start off with the network. Most apps that I'm sure you guys have built have a networking or cloud component. I already mentioned we're using SSL, but let's make that stronger. I'm going to use OKhttp library that from Square as an example in some of these some of the code samples, just because it's kind of the de facto on Android. But also you can do this with HTTP URL connection and the other kind of HTTP libraries. It's just easier with OKhttp. So the first thing we can do, is make the connection stronger. We won't go into all the kind of all the details of SSL. We could do a whole presentation and maybe even a day's course on that. But in a basic sense, SSL has to support lots of old browsers and lots of different configurations. And so it can be made by attackers to sort of fall back to using lesser cipher suites and lower kind of quality encryption effectively. What we can do very easily using this connection spec object when we create our HTTP client, we can just make sure it's using only the strong cipher suites and the strongest kind of TLS version. And if you're not sure what the server supports, SSLLabs.com have an SSL test. There's other ones available, but you can just point your API endpoint at that, and it will analyze that, give you a report, like a scorecard. But importantly, it'll tell you what cipher suites and things are supported. It even gives you what Android versions support those as well. So it's quite a cool way if you don't have any kind of visibility or dialogue with the web guys, which is often the case in sort of agency work. You're kind of isolated from the client and the API. It's a way of sort of doing that. So that will help you, increase that connection, and it's on a budget. It's meeting a requirement. It's not much extra code that we're introducing. The next thing we could do is there's been various different SSL exploits over the past 2 years. Heartbleed, Poodle, issues of OpenSSL, and one of the issues with Android is that Google can put a patch in to the open source project, and that'll take weeks or months to trickle down to OEMs and have carriers have their say and do their testing before it actually gets on devices, even if the devices are still even supported. So what Google decided to do was they built into the Google Play services a way to update the device's SSL provider. So it's really simple to do. It's just like one line of code. And Google Play Services is supported on, I think, everything from Android 2.3 upwards. So just that's the only line of code you need to run, and you'd sort of run that on your application, on Create or something like that. If there's if the device needs to be updated, it will go and do that update. There's a whole training article about how to do this and how to do it asynchronously, but I just put a quick example to show you, it's literally a one-liner. The next thing we could look at doing from an SSL point of view is to use something called SSL Pinning. And for those kind of not familiar, Mr. Clippy will tell us a bit about it. I should do a little impression, but I'm not going to. So pinning basically limits the certificate authorities that we trust. The problem is on devices, every Android device that ships with well over 100 certificate authorities. And if any one of those is compromised, it's happened in the last couple of years, or even if there's like a malicious employee at the certificate authority, and also there's been kind of links with governments kind of having access or being sort of in bed with some of the certificate authorities and having access to root certificates. With a compromised certificate authority, then it would mean that even if you're doing all the great, the right SSL validation, that you could still be, users could still be man-in-the-middle attacked, because it would appear as a trusted certificate authority. So what you can do is you can pin the connection, and that basically allows you to sort of fix the certain SSL certificate chain that you trust. You can either pin the actual certificate, which isn't so good, because if you renew that, when you renew that certificate, that will change, and you'll need to do an app update. What you can do is you can pin the public key, which doesn't have to change between updates to the certificate. And this is really easy to do. Again, using OKhttp as an example, we'll just create a certificate pinner object, and you just pass in the pins, and the pins, there's 4 pins there as an example, and that's for the whole certificate chain. If you want to know how to get these pins is just like it's just a SHA-1 of the public key. It might sound scary if you've not done this before, but so I wrote a little. If you follow that bit.ly link, I wrote a little util on a Java util on GitHub, and it's just a jar, and it will go and get that and output to the console that exact output. So you can just cut and paste that into your code. So it's really simple to use. I definitely would say make sure you're using the latest version of this. There was a vulnerability found in the last couple of weeks around pinning and how to sort of beat it. So definitely use the latest versions. I also say a little bit of caveat with this is that if you should do pinning with the blessing of your TLS administrator, your server guys, because if they change stuff, they could break the app. But just as a caveat. Lastly, on networking, let's look at something I know a lot of Android guys in the audience will love, WebView. So this app was using WebView in an okay way, I guess. We were using it for the help, for terms and conditions, for privacy policy, kind of legitimate stuff that you don't want to do an app update every time the privacy policy changes. And so, but those kind of static pages don't need some of the kind of risky settings that tends to be associated with all the vulnerabilities you hear about with WebView. So what we can do is just really simply disable JavaScript, disable file access, and actually we can go one step further and just only access, whitelist the domains and things that those web views can access. I wrote a simple gist that's there you can access, which just does that for you, and you just pass it a string of an array of URLs that you're okay with accessing, and yet it'll block access to anything else. So it's really simple, and it's just stuff you can do to sort of harden your web view, and that's going to be less vulnerable to things like cross-site scripting and other kind of vulnerabilities that tend to come from JavaScript, the JavaScript interface. So that was the kind of like networking side of things. Now we're going to look at moving on from that. We're looking at the integrity of the device and any data that we're caching, the data at rest. And when we're saying device integrity, we're really talking about our friend root. And there's nothing inherently like bad, against root. I mean, most of my test devices are rooted, but the fundamental thing you have to accept when your device is rooted, that the system sort of sandbox security no longer applies. Attackers, malicious apps, the user can be elevated to root privilege, and instead of having a sandbox where only your app can read and write, suddenly now attackers can potentially read and manipulate that data. So that's a potential risk. So what can we do to sort of like flag that up to the server or to the user? There's a couple of things you can do. I co-wrote a library called rootbeer, and that does, basically it was a collection of all the root checks we could find online, plus a couple of ones we'd come up with ourselves to check for root. And you could use it in conjunction with the safety net API. And the safety net API is one of those completely, I feel like it's one of those cool, I guess because I'm interested in security, I think it's cool, but it's one of those things as part of Google Play Services that doesn't get enough press. And it does some cool stuff. But it was a very simple API, but it's done in a, I didn't think it was done, it was simple enough. So I wrote a little wrapper to go around that to make it even easier, to make it just like one call. And that'll do a test, and that tests the device for various different vulnerabilities it could be susceptible to. Things like we mentioned earlier, like out-of-date SSL providers. But one of the side effects of the safety net API does is actually it identifies and flags up rooted devices, although it's certainly not sort of sold as a root checking API. But yeah, you could use those in conjunction to give you an indication of what kind of the state of the device, and then what you do when you detect root is very subjective. It depends on the app. In this context and this app and the way we were kind of sneaking these things in, there wasn't a lot to do. Analytics event, maybe you'd warn the user that they're on a rooted device and it won't be as secure. Maybe you absolve yourself of risk and get them to hit a disclaimer. Maybe, probably more securely, you wouldn't store any data at rest, because on a rooted device you can't guarantee that security. It's really dependent on your app. A couple of things I should say as caveats around this is that when a root is effectively God, if you think of it as that way. So there's no like 100% way to do a check for root. There's always ways to trick it, but we found with rootbeer you need to use a couple of the different root cloakers together to break it, and also with safety net. I think there's some people have developed stuff to try and trick that recently, but yeah, it's just, again, it's kind of raising the bar. And in the context of this, trying to do minimum effort, maximum impact, these kind of libraries are drop-in and one-liners effectively. Let's look at some of the data that we're storing. And I'll come back to why I've sort of said obfuscate the data there at the end. But so the app was using shared preferences to store like things like access tokens and maybe to remember the user's email address and some other kind of arbitrary bits of information. And for those who aren't familiar, shared preferences is just like an XML file, it's backed by an XML file. But on a rooted device, if you can access that, you can quite easily change data within that. So if you can imagine if you had like the number of coins you had available to make in-app purchases with or something, if that was easily readable, you could just go and edit that, in a separate app, let alone it being reverse engineered. So what I did was I just replaced it for a library that I knew well, secure preferences. So you might note that I helped write that. Or you might want to look at Hawk. It's got more stars, it's got a logo, and it's got a better name. So it does the same kind of thing. We were storing data. The app needs to work offline, so we were caching some data. So we were using SQLite for that. So a straight replacement for that to make it kind of relatively secure would be SQL Cipher for Android. It's pretty much the same API, but you just need to sort of pass it a password, and it uses that to generate an encryption key to encrypt all the tables and the files. And that's great, because then if anyone extracts the database, from a vulnerable phone, that they're going to need to reverse engineer the app to find out how that key's generated. I thought I'd mention Realm as well. That has an encryption option under the kind of the same principle. You give it a password or a key, and it will use that. And so the reason I said obfuscate, like in brackets, is because we're generating the key on a per app basis and storing the key kind of in the same place, albeit a little bit obfuscated. So it's not kind of like truly secure, because if an attacker has that device, has the sort of target device in hand, they can go and find that key. The better way to do it, and this is the kind of way I would do it if I had more time and it was a different context, is to not store the key at all. Is to use like an in-app pin code. So I would use that to then generate using password-based encryption. I'd use that to generate a key, or I'd tie it into the Android key store, so I could use the devices pin. And recently, you can use the fingerprint reader to do that. So that's not how we did it in this, but that's I just thought it worth mentioning that for how you should do it in our ideal world. So that's the kind of data kind of handled, hopefully. We spent time on the UI, and then the sort of the last sprint we were getting close to going live, and so we start thinking about what we're going to do. How's the APK going to behave, and how's that going to sort of be when it's sort of out on all our devices, all the customer devices? So that's when we start thinking about the integrity and the protection of the actual binary. So to start off with, we do a really kind of simple tamper check, and this involves basically checking the digital signature of the APK file to make sure it's what we expect. And the way that works is that all apps on Android have to be digitally signed, and we all know this because we have our debug key store and we have our release key store. And they have to be consistent, and we've seen that if you've ever tried to install your debug build on top of your release build, and if you've got the same app ID, you'll see that, I forget the error, but it's to do with mismatch of certificate. So we know that has to be consistent. Every update to our app has to be signed with the same key. So we know that at build time, so we can get the signature very easily using the key tool. If you can, see that. And the key tool is just part of the JDK, so it's very, you all have it installed. That'll give you the SHA-1. You can just embed that in your app. I'm just talking about putting it in a string. And then at runtime, you can go and get that signature from the package manager. You hash it so it matches, the same hash, and you can compare that. And so the trick is, because if I've taken your app and reverse engineered it and added some code or removed some stuff, I'll need to re-sign that, and that signature will be different. So that's the kind of point. So you're checking to make sure that no one's sort of tampered with your app. Other options, things you could do around tamper checking, checking if the app is in a debuggable state, checking if you're running on an emulator. You can also do like a CRC32 check of the APK file. I haven't actually used that in production just because it changes for each kind of app update, whereas this is just write once and it's done. And I kind of tend to have it so I would have a signature in my build config fields. So I would have a signature for my debug key and one for my release key. And you can use that in Gradle with flavors, and you just have a different one defined. So that's it for this. Is a really simple tamper check. Obviously, or maybe not obviously, but if someone is reverse engineering your code, they can just take this tamper check out. But it's just another level of kind of skill and effort they'll need to do that. We can make that harder by obfuscating the code. And most of you who are Android developers in the audience will have heard of ProGuard. It's a Java code obfuscator. It's part of the SDK, and it's really easy to use, isn't it? You just enable mimify enabled equals true, and all your problems are solved. Everyone else had that same experience? Yeah? No. I love this graphic, and I hope it's a bit pixelated, but I thought it was very true of my experience with ProGuard. And it certainly was the hardest thing I did of all these kind of little bits of stuff I'm trying to sneak into this app to make it more secure under the radar. The ProGuard stuff was definitely the most time-consuming. A couple of tips when you're working with ProGuard. Definitely, when you're adding new libraries and new dependencies, most good open source libraries will have ProGuard exclusion config if it's needed. So I tend to add them as I go along, build your config file up, and also run it early, and start building that into your release build as from sprint 1. I use it a lot to strip out log statements, and I don't have to worry about potentially bleeding sensitive user information at runtime. That's all stripped out. I have found it generally is a bit trial and error with the errors and the stuff you get from ProGuard in the console. It's basically a case of just excluding and ignoring, and getting it to compile. That's a big hooray. And then doing a full kind of regression test and making sure that nothing's broken. Generally, though, I guess if the first success is getting it to compile, then if it runs without crashing, even just starting up, that's you're halfway there. There's an interesting Gradle plugin that will automatically go and get some of those ProGuard configs if you haven't got them. That's pretty cool. Although it hasn't got a massive amount of libraries that it supports. I should just mention that your crash, if you're ever unfortunate to get a crash in your app. I know we're all perfect developers and never have bugs or crashes in our apps, but occasionally it happened to a friend once. But your stack traces are going to be obfuscated as well. So working out what crashed when you've got a class A method B with variable C is quite difficult. So what you have to do is use it. There's a tool called retrace, which will retrace that stack trace back into like a normal stack trace that you're used to seeing. But if you're using services like Crashlytics, it does it automatically for you. It will automatically upload your mappings file and automatically deobfuscate your file. I can't recommend Crashlytics enough for that kind of feature alone. And actually, the Google Play Store has started supporting mappings uploads as well. So you can use, if anyone does use the error reporting the crash reporting that's in the Play Store, it now supports obfuscated crashes, which is pretty cool. And lastly, if you've got a license for it already, I would certainly recommend looking at DexGuard. One of the cool things that can do, like when we a couple of slides ago, we talked about tamper checking and putting in the certificate, the hash of the certificate to check. Well, that's still in like fairly plain text in the file. But with DexGuard, you can use like string encryption and class encryption, and it makes that a lot more difficult to find in the APK file. So that's what I've used in the past. So yeah, it's something to sort of have a look at. It's a paid option, but it's certainly worth looking at. And the great thing about it is that once you've gone through that pain of using ProGuard, getting it configured, getting it working, DexGuard is just a case of like it uses all the same config, and you can just do some extra kind of config for making it even stronger. But in essence, just by switching to using DexGuard, it uses the same config. So that's kind of it for our app. We put all those things in. We hit the deadline. We passed the user acceptance testing. We hit that magical button, and we all know what follows next. It's profit. But so what? We stuck all these security changes in. But what did it? What was the difference? What was the end result? Let's start with the negatives. We definitely we added more code to the project, so we definitely made it more complicated. We made the APK file size larger. Especially if we're using something like SQL Cipher, that adds like 7-8 meg to APK file size. We've definitely slowed our start time with generating encryption keys. That can be quite lengthy on some old devices. The encrypted data is only really obfuscated because we're storing the key as well, so it's not like truly secure. As I kind of joked and mentioned, the ProGuard config was time-consuming, several late nights getting that sorted. And sadly, we're going to get no credit for our work, for our hard work, because we did it under the radar. But on the plus side, the app is a lot less vulnerable to man-in-the-middle attacks. The web views are safer and less vulnerable to things like cross-site scripting. Just curious rooted users can't go and change our settings of our preference data and our database. They're going to need to reverse engineer the app and work out how the keys are generated, how the data is encrypted, to be able to decrypt that. And in general, rooted users are going to struggle because we've added those checks. We've hampered people the recompilation of the app because we've added a tamper check. And actually, the whole understanding of that decompiled code we've made more difficult via the obfuscation. So as I ask myself at the end of every day, do we win? We know the app isn't 100% secure, but that wasn't the objective at the start. We were aiming for minimum effort, maximum gain. We've kind of dramatically increased the skill level of the attacker that is going to need to sort of compromise our app. Certainly above that of an automated attack. And crucially, it's above someone just reading a blog article about how to reverse engineer Android apps and being able to be able to apply that to our app. It's taken it out of their field sort of thing. So that's like probably cut down a lot of the potential attacks. We've also crucially increased the amount of time it's going to take to circumvent. So even a skilled hacker, it's going to take them time. So did we win? I think so. I think we leveled up our app security. We know we could make it better, but we've acquitted ourselves. And we've kind of we've saved our reputation, and perhaps more importantly, we've saved the app's users and potentially their privacy. So when you kind of think about it, and you go back to your day jobs and stuff, and you think about what can you do when there's no sort of support for adding security stuff. We talked about 8 things today that you can easily do, and you can just drop in pretty much most of these and sort of get working. And I guess kind of almost lastly is that should you do it? And I guess sneaking code into a project under the radar without anyone knowing in a professional environment is less than ideal. And I guess you're an adult. It's up to you guys to make that call. Hopefully, by seeing this kind of presentation, you can see that some of these enhancements are actually quite straightforward. You can leverage open source libraries. These are all, I forgot to say, but they're all commercially viable. So maybe that is enough to convince the powers that be, the stakeholders, to actually spend some time and put these in place. Just before I wrap up, I just thought I'd mention about Apple. A lot of these techniques you could apply to iOS apps. Don't be mistaken, just because of the app approval process and the fact the OS is a bit more locked down, that they're immune to app security issues. It's not the case. SSL pinning, hardening, totally could be applied. Jailbreak detection checks come with the same caveats as root checks, but the same principle. You could additionally encrypt stuff when you're putting it into the keychain, and you can use obfuscation as well. People don't tend to because it's harder to reverse engineer iOS apps, but people still do it, so make it a little bit harder for them. So there's some resources for anyone who downloads the slides, and that's it. Thanks very much for listening.